service for Roger. The family has notified us that it will be on Saturday, the 24th of this month. It'll be at the Downingtown United Methodist Church. Visitation is from 10 to 11 o'clock a.m. and there will be a memorial service at 11 o'clock. And so anybody that would like to attend, please feel free to do so. I'm sure it would be a nice show of support to Roger's family and his close relatives and friends who will be there. We will be sending out a notification to everybody soon about the time and the location of the event. So with that, I'd like to turn our meeting over now to Don Knabb, who's going to talk to us a little bit about some upcoming events and has a little presentation for us.
Yeah.
Take it away, Don.
Okay. Thanks, Dave. Okay. Steve, you see that okay at home?
Yes.
Yes.
Okay.
I
You know what
see.
the-
Yep, looks good.
Okay,
Mhm.
these are the upcoming events. So sort of hidden up here, but what it says up there is, thank you to everyone who came out to Battle the Clouds Park. Friday, a week and a half ago. We had about 10 scopes set up. I think it was about Dave, right? What did you say, about 10? It was great, really good response. They limited, this is for the Malvern Library. They limited the registration to 50, but about 65 people showed up anyway. So it was a really good night, from everything I've been told. And we had a beautiful moon, Saturn, Jupiter, probably a few clusters, I would guess, right? Lagoon Nebula. Lagoon Nebula, wow, okay, all right. So it was a nice event. So thanks to everybody who came out. It was a really great turnout. So in 3 days, this Friday, we have one with Star Farm Park. It looks like the weather's going to be good the next couple of days. So this is like between Westchester, Downingtown area. Go out toward Downingtown 322, Scuffle Level Road, just up the road a bit. It's really not far at all from Westchester. It's a good site. It's not perfect. There's not a lot of parking. But the nice thing is when we park, we can set up right behind the cars. There's no carrying equipment like we had to do at Battle of the Clouds. So I guess we're up to 4 people now, I know, coming out. So that'll be good. That'll be enough. I know Dave's coming out and Kathy, you said you'd be there? Oh, Don Miller, I looked at 5. No, Kathy can't do it. That's right. Chris Trunk is coming out and Mike, you're coming out. So we're up to like 5 people now. So we're good there. So we're good. But that's a nice place. And they are limiting attendance to 40 people, which means maybe 50 will come out. So that's what East Bradford Township. So this Friday, and also I'll watch the weather and send a note after. Right now the forecast is pretty good. The next couple of nights look pretty clear. So York County Star Party. It's a small scale regional gathering. I know Dave, you've been there. Pete Kellerman was there. Sue Johnson was there, right?
Yep.
And this is like last year, or no, year before last. Year before last. So it's small scale, but it's growing. It's funny. It's the York County Star Party in Lancaster County. That's where they hold it. But it's only like a little over an hour drive, which is nice. So you don't have to go 5 hours to Cherry Springs. Nice flat field, a decent horizon. The sky isn't great. I would say sort of like BRC. It's better than Westchester, but not a whole lot. It's no Cherry Springs. But there's nice hiking. And it's one of the few places you can go and look down at eagles, or when they're flying down, look down at them because they're so high over the Susquehanna. You don't have to camp. You can just come out for the evening, but you have to register. And then at the end of October, I'm really looking forward to this because Barb and I will be there for this one. This is Wolf's Hollow with Ackland, and they're going to limit that to 50 people. Because a couple of years ago, they had like 150 came out. So they're going to limit that to 50 people. It's an excellent observing location. It is some of the best I've seen in this county. Far better than BRC. Really good wide horizons. And we will set up right along this road. We'll park along the side and we'll set up our scopes here like we do at Nottingham. Same idea. And that works for a lot of people. Just go down the line. Don't have to go in any tall grass. We'll be right by the road. And it's a really neat site. It really is. And the rangers there are really nice and helpful, friendly. And we do have two more Red Flag Alliance observing days, Friday, October 14th and Friday, November 18th. So let me stop that share. I guess we'll take a quick look at the night sky. Now I don't have COVID, I have a cough, so I'll see how far I get here. But this is the sky. Tell you what time. Tonight at 8:40. So it's about, I said an hour ahead, so it'll be dark. So if you get out like later this week or this Friday, this is the spot I first go to. This is the southern sky, which in another month or so, these guys are all going to be down. So take the time to look at it now. My favorites is probably Ptolemy's cluster is one of my favorites. It is really bright and it has got 30, 40 stars probably. Looks much better in the eyepiece than it does here on the computer. My next favorite in this area, it's smaller because it's further away, is Butterfly Cluster. And you can sort of see this is like the head, the body, here's the wings going out. And in the scope, it really looks like a butterfly, I think. It's really beautiful, beautiful open cluster. And even in our light blue skies, you can see these guys. Like Chris said at the event Friday a week ago, had the Lagoon Nebula, which is a big bright nebula, beautiful to see. Just above it, not quite as bright and big, but the Trifid, equally famous. I think my favorite in this part of the sky is probably M22. This is one of my favorites here. This is probably the best globular cluster in the northern sky, except that it's so close to the horizon. If it was overhead where M13 is at, it would be truly spectacular. But it's nice anyway. Another spot I really like to look at is this. This is the small Sagittarius star cloud. The large Sagittarius is this whole area. This is M24. And it's not a star cloud. It's a hole. It's a hole looking toward the center of the galaxy. All this would look like that if it wasn't for intervening clouds of gas and dust. So that's actually a window into toward the center of the galaxy. Of course, the Omega, which I'm used to calling this the Swan. I'm used to calling this the Swan Nebula, sort of see a swan shape in this when you see it the right way. And the Eagle Nebula, this is the famous Pillars of Creation, which you can't really pick out too much in the scope. Maybe when Dave takes a picture of it, you can. But there is the Eagle, and these are the Pillars of Creation from the famous Hubble image. So that's pretty much, that's where I go this time of year, because we're still going to, one other one, the wild duck. One of my favorites, the wild duck. And this is such a tight open cluster, it's mistaken for a globular cluster sometimes. That's really one of my favorites also. They're all my favorites in here, you know. I will stop that share. John, are you set to go? You're muted.
Not anymore. How are you all doing?
Good, good. How about you?
I'm doing great. And I don't know if you'd mentioned this to Dave or any of the people, but a week ago, I was looking forward to being there in person. I'm really looking forward to it. It's been so long. I mean, really long. I haven't seen most of you in person in years. Any of you that have kids will understand that within that week, one of our kids gave us a call and we ended up in Portland, Oregon for a couple weeks. So we're out there and I'm using my son's home office tonight for this. So hello from the West Coast, and the fires are getting a little bit better. I had a couple days earlier this week where it really kicked up the allergies, the ash in the air, even though it's not near Portland. It's amazing out here. They had they've had I think now 68-day straight days of no rain. And you tend to think of Seattle and Portland as wet places. It's the second longest dry streak they've ever had. So climate change is alive and well. And things are pretty dangerous in places. At any rate, let's get started here. I'll put the slides on.
John, I'm gonna try leaving the microphone here live. We'll see how it works. If it gets to be a bother, just let me know, okay?
Okay, you let me know if it's a problem. Can you hear me all right?
We hear you fine. It's great. This is working really well. Okay.
All right. So of course we'll start off. Can you see the picture here?
Yes.
Yeah, we're good.
Did that share?
Yes.
Yep.
So you see the famous, world famous astronomers Jennifer and Leonardo there in the front row. And I imagine a lot of you saw this. There's the nasty president, Meryl Streep, in the back row. And this would have been incredible 10 years ago, but basically it was a story of a near-Earth object that these astronomers discovered was going to impact the Earth with certainty. And they told the president, and the president figured out a way, not just cynical, but worse, to get everybody to rally around the, what's the word for it, conspiracy that she had in mind, and not look up. So we're going to talk about the fact that we have got something coming up, and it's very important that you do look up. So let's see, get my slides working here. And so you see there on the right, an artist's concept of an asteroid, not a big one, and a real look at what the DART spacecraft looks like, which fortunately is well on its way to a successful impact, which will take place. And you can look up, but you won't see anything because it's way too far away. And even with your best telescopes, as we'll talk about later, nobody on Earth or any of our space telescopes is actually going to see the impact. But we can look at the double asteroid system that gives us this name, double asteroid redirection test. And it's a very important test of our planetary defense mission. And it's got an international side to it as well that we'll talk about briefly at the end. But at any rate, I wanted to give real credit to a very special organization, not JPL, but APL this time, is the designer and builder of this spacecraft. And you may know them from previous missions like New Horizons. They've been around a long time, just like JPL, and I can attest to it personally. In 68, which is, what is that, 54 years ago, I launched a unique booster configuration in Atlas and a burner 2 upper stage from what is now the Vandenberg Space Force Base. At the time, it was the Vandenberg Air Force Base. And we launched, among other satellites, a small APL satellite. And none of the 12 ever made it into orbit because the heat shield didn't open, the kind of thing that happened in the first decade of the space age. So APL doesn't actually remember me from that, but I was the launch director on that. And it went into the South Pacific and everything was lost. So this time around, APL is going to have some success and they're actually going to hit it. So it's a bunch of other organizations as well that I'd like to just give a moment's credit to. JPL was very much involved, lots of NASA centers, and as you can see, a number of commercial companies, universities, and research organizations as well had a hand in this very important asteroid deflection test. So this particular slide is a reminder of some of the things that you may have heard me talk about in my NEO near Earth object talk, which I think I gave to you folks 3 or 4 years ago at least. And at the time, we talked about the organization in the middle of the top there. The International Astronomical Union has a minor planet center, and they're the world's repository, if you will, for all small new objects that get discovered, to give them a firm number, give them orbital elements that are updated hopefully on a regular basis. So anything that's flying around the sun, which is pretty much all the stuff in the solar system with the exception of a few moons, is a minor planet. And so that's where the near Earth objects get logged and get recorded. And the mission of planetary defense, which has now been officially stepped up to with a planetary defense officer in Washington and NASA headquarters, has also been matched by other developed nations. The UK and I think maybe as many as a dozen others now also have a planetary defense program. And they all cooperate, not only in sharing the information from, but contributing to the first block there of search and detect and track. So we have very large ground-based telescopes for the most part that are upping the number of NEOs all the time. And you'll see those statistics in a second. You move around there to the lower right, and not only do we want the optical look, but we want to get some infrared and radio information, which we do from some telescopes, because that helps to understand the shape and the composition in better to some degree. The NEO-WISE actually, as we'll see in a minute, is very useful to look in the infrared, where it can see objects that are cooler in a brighter way, and therefore see things that optical wavelengths, the visible wavelengths, miss. Down at the bottom there is a note that as these programs have collected their data, they've cooperated and formed working groups like the IWG, the International Working Group. They have not just, I think, maybe annual or at least frequent symposia and conferences. And they also have international exercises to test out how the civil defense will work, to share information and prepare if there's ever going to be a NEO problem. And then finally, we get to the mitigation box, which is hopefully going to be the answer to any of the bad actors that are out there near us that are on a collision course. And so we've finally now commissioned, designed, developed, and launched the first of our asteroid deflection tests, the DART, double asteroid redirection test. And we'll just pause here, especially for some of those that may not have heard my earlier talk, to show what it is that's helping us see the NEOs at this point. In the 90s, we were relying a lot on the MIT survey telescope. We didn't yet have the funding that started to come in the late 90s, and it's continued ever since, to fund some very large telescope sky surveys. And you can all pretty much picture the way this works. You have a telescope with a field of view, and it repeats exactly the same field of view, stepping across the entire sky over and over again. So you get revisits, and you can look for objects that have changed as opposed to the fixed star field, and discover lots of near-Earth objects that way. And so Catalina and Pan-STARRS have contributed the most in the last 15 years or so to the numbers that have grown. And up in space, we've got a telescope that was launched by NASA as the WISE, or Wideband Infrared Space Explorer. And therefore, it's able to see in the infrared, which is better to see these darker, cooler objects. And also, it got repurposed to be dedicated to a NEO mission after the WISE mission was completed over a decade ago. So it's improved the count a lot. And these dark objects are not unlike lumps of coal, they say. The albedo is really low for asteroids, so they're not easy to see. And it takes these big telescopes staring a lot to see them. And thank goodness we've got an infrared one up there looking too. So this slide, which I did show before, you may remember, it's kind of an interesting way to look at the count of not just near Earth objects, which we care most about, but all the asteroids. And so if we go all the way back to the beginning of the 19th century in 1800, you see the year there, which will change when I do the animation. Pretty much in 1800, the telescopes weren't such that we'd found much in that area beyond Mars, which is the asteroid belt, the main asteroid belt. And so shortly after 1800, I think in 1802, maybe, Ceres was discovered. They called it a planet. They found a number of other large asteroids, which also got called planets alongside of Jupiter and Saturn for about 50 years. And they decided that that wasn't going to work because they were going to find a lot of those. So they stopped calling them planets, and they're just asteroids until the IAU decided that they would call some of them dwarf planets. So at any rate, when I start this up, you're going to see lots of the blue ones, the small blue ones in the main asteroid belt in the first 100 years. And then as it steps forward, you'll see after each time how many more got counted. And by the middle of the 20th century, we started to find near Earth or asteroids. And then we found lots more as we get toward the end. So here we are in 1900 with some. 1950, before the space age, we found lots out there and only a few close to us. By 1990, before the funding, we'd found a fair number of NEOs. And after the funding began, the numbers just accelerated. And this particular slide ends in 2013. And the count at that point, you can see there the Minor Planet Center has over 600,000 that they were tracking. As of that point, most of those are asteroids in the asteroid belt, but about 10,000 NEOs. And so remember that as I put the next slide up, which says that in the 9 years since 2013, we've gone from about 10,000 to 29,000. So we're at a rate now of finding about 3,000 new near-Earth objects a year. And most of them, we can be glad that Congress finally decided to have a serious program, and that's led to finding almost all these since 1998 when the program office opened. There's a term PHA that you may have heard, and those are defined by these parameters: greater than 140 meters, which is pretty large, and relatively close. And that is, as it says, a relative term. It's not like saying it's going to miss us, as you might think from some of the headlines in some of the schlock science journals that say, you know, gigantic asteroid headed for Earth, and when you look it up, it's going to miss us by 3 times the distance to the moon or something. But relatively close does mean something like, you know, not many lunar distances. And by missing us, we mean that all of these either just barely reach out to Earth in their furthest reach, their aphelion, or they cross Earth's orbit. And so, of course, what we're watching for is the ones that don't just cross it, but happen to intersect it when we're there. The ones that we really worry about are those that are a kilometer or larger. And we think they're about a fact. And that, of course, is the dinosaur killer, which happened 65 million years ago, we believe, from the geologic record, just north of the Yucatan Peninsula in the Gulf of Mexico, and left a crater about the size of Lake Erie, but many, many times deeper. And that caused the extinction of lots of species, including the dinosaurs. The next size down, 1 kilometer, we believe that the 4 that we are tracking now are all that there are there because they're easy to find. The next size down, the kilometer size, we believe would literally wipe out our infrastructure and therefore could cause the collapse of civilization for some period of time, because we depend so much on that. And we've all seen that there is sort of a fine line between chaos and order at this point. At any rate, we haven't found all those, we don't believe, and these are the ones that we've been chartered to find all of. I don't know who has come up with the estimate that there are 1,000 of these, but they estimate that we found about 90% of those. I'm sorry, yeah, 900 of these, and that we hopefully can pretty soon find the other 10%. I will note, I don't have time to show it, but there's a new NASA NEO survey telescope to be launched and put at the L1 point, which is that stable point between the sun and Earth, and it will look out towards Earth, and that will take care of the region of search for those that we can't see at this point because they're too near the sun every time we go to look for them. And so hopefully with that new spacecraft, and I think it's to be launched in about 5 or 6 years, we're going to be able to close out with higher probability a lot of these. Then we'll step down to the sort of medium sized, and these are still in that range called potentially hazardous. And we've got some examples of craters around the world that are examples of this. And they can cause a very deadly impact over a geographic area, even a state-sized area. We think we haven't found even half of those, and there are lots of them out there, but they're in the catalog now, the ones we found. And then you get down to the less hazardous ones, although I have to say, of the 25-meter size, we've seen a couple of recent examples of that we talked about in our previous talk. Tunguska was a little over a century ago in eastern Siberia at 40 meters. It was an airburst that fortunately didn't cause fatalities, we don't believe, although there were indigenous in that area. But it did knock down tens of millions of trees and was quite an explosion. Chelyabinsk occurred about a century after that, and you see the frequency line there. These are obviously frequency lines that are estimated by the craters we found around the world and the dating of those craters and so on. So we think these 20, 25 meter size, maybe a little larger like Tunguska, will be about once a century. And Chelyabinsk happened in Russia the day after Valentine's Day, 9 years ago. And it was, if it had been over a populated area, as opposed to about 30 miles away at altitude, it would have caused deaths for sure. It caused 1,600 casualties as it was. Okay, so that's a quick look. And let me finish by noting the Barringer crater out in Arizona, which a number of people have seen since it's so near the interstate out there, with big signs advertising it as you approach the exit. And the Barringer crater we estimate to be a metal asteroid that hit at a very steep angle and created a crater 1.2 kilometers in diameter about 50,000 years ago. And it's, I think, useful to think about what the impact on people would be from that size crater if it hit near us. And so here's a look at the damage radii. And so within that red circle there that goes out to about 6 miles is the fireball range, which means nothing living is going to survive. Out to about 15 miles or 24 kilometers, lots of people will be killed and lots of people will be injured. And even out to about 25 miles, you're going to have hurricane scale winds. So that's interesting in the Arizona desert. But let's look at what those circles mean over a populated area like the District of Columbia, where everything within the district would be in the fireball. And so we're not going to pause and consider the fact that nothing would live in the heart of our capital there. We'll go out to the next range and note that those Virginia and Maryland suburbs would be pretty much impacted with lots of deaths and casualties. And all the way out to the Chesapeake Bay, you get hurricane force winds. So one of these, frankly, not that large, 50-meter, is going to cause a lot of human suffering if it happens to hit in a very populated area. In one chart here, we're going to talk about all the techniques that have been studied now for a couple decades to deflect asteroids, which is what we'll want to do if we find one that's got our name on it. And so the friendliest of these techniques that they've come up with, other than just for the small asteroids, where we talk about using civil defense measures to evacuate areas and so on. But by the time you get up to 100-meter diameter, up to maybe 150, 200, there's a green area, kind of the friendly approach to deflecting asteroids. If you have enough years, and you see the time scale across the bottom, says that if you've got 100 meters and you've got something that's 2 decades out, and with our orbital calculations, we're able to easily predict orbits that far out. And they change all the time. That's why we check them all the time, because they can be perturbed. At any rate, the tractor would be simply sending a high mass asteroid spacecraft out there, parked next to the asteroid, and then sort of slowly over a period of months and years, just back the spacecraft away from the asteroid and use the mutual gravitational attraction to change the velocity vector of the asteroid enough so that it misses the Earth. And we think for some of the medium-sized ones, if we have enough decades, we can use that technique. But otherwise, we're going to have to hit it with something. And the nuclear is what everybody thinks about first, just like the movies Armageddon and Deep Impact in the 90s, which were, by the way, totally unrealistic. If you send the nuclear device out there, not only will it be dangerous to send such a device out through the atmosphere, since if it happened to not make it through the atmosphere, we might have a problem with scattered radioactivity in the atmosphere. But if it gets through and gets out there, what we think now, since we think an awful high percentage of the asteroids are rubble piles, that we may end up not with one huge problem, but with a number of medium-sized problems that are still on their way towards Earth. So it's not even clear that we want to use that when we have to. But the kinetic technique simply means hit it as hard as you can with something other than a nuclear device. And so finally, as the National Academy of Sciences recommended a little over 10 years ago in their report, NASA has funded and then developed and now launched the first test of a kinetic impactor. And that's what we're going to talk about. That's the DART spacecraft. And so let's take a look at the target. This is the double asteroid system, and you folks are familiar with binary systems where the smaller orbits the larger. The larger is quite large. Didymos can be seen by ground-based telescopes from Earth. And here's a comparison so you can understand its size. Its biggest dimension is bigger than the World Trade Center and quite a bit shorter than the Burj Khalifa, but it's much more massive than either of those. And orbiting around it is the real target for DART, and that's Dimorphos. And Dimorphos is about that size, 163 meters, and in mass, it's about the same as the Great Pyramid. The one I like to compare it to, though, is the Colosseum. And there it is hovering over the Colosseum. And that's what we're going to hit with DART. And so now let's look at DART's size. And it's down there, 19 meters, about 60 feet long, Most of that is solar panels, not very big in length, a bit longer than a bus. We'll talk about the mass of it when I show you the spacecraft. Here you see the moving star background as the ground-based telescope down in Chile stared at Didymos, and we aren't able, with any telescopes we have yet, to really resolve Didymos, let alone see Dimorphos. On the right is a view of Didymos that isn't actually an optical image. It's taken from the radar data that we've had, as well as the light curve data that you'll see in a minute. So that's kind of what we think Didymos is going to look like. What we think Dimorphos is going to look like is in the center there between the question marks. We don't know. We have taken the dimension that we have for it based on the light curve data and some other asteroids about that size and some other things to model it, and guessed on this. So there's a lot of press you're starting to see now. The media will get excited about an impact of an asteroid. So you may very well see this picture over the next, 13th to the 26th, almost 2 weeks before the impact. And you guys are going to be the insiders that know that we don't have a clue if it actually looks like that. So now I want to just show you a quick video, starting with the very successful launch last November from about a quarter of a mile where I launched an APL satellite in '68. This is the launch on a SpaceX Falcon. And so here we go. And what you see is the heat shield coming off successfully, the dart being deployed, and the solar panels rolling out about 30 feet on each side. The lens cover comes off of the ever important telescope camera. Here's a look at the double asteroid system in orbit. And as it makes its close approach to Earth, right there is when we're going to impact it. And there's another spacecraft that's a small CubeSat that you see there being deployed about 10 days beforehand on the 16th. And it will fly behind DART so that when we have the impact, guided by the automated camera and software system on board, the CubeSat will fly by a few minutes later and take an image of what we hope will be a nice crater that we create on Dimorphos. So here's a look. That one going around, that's not two asteroids, that's a bilobe version of Dimorphos. And so we have been tracking the period and have the period very accurately calculated. And when DART arrives on the 26th, it will have deployed the Lichia Cube CubeSat. It will impact, the CubeSat will fly by and take some pictures that'll give us some information, but the initial big information will come from calculations of the new orbit to see just how much we were able to change the current orbit. Now the current orbit is about 11.9 hours. And so we're calculating that there will be at least a 1% change in the orbit, which works out to about 6 or 7 minutes. And I've seen some things from online that have indicated there's an estimate that we might actually get a change of 11 minutes in the orbit. And remember, this is a test of a kinetic technique. We're going to learn a lot about the surface and what's under the surface of a small asteroid. We're going to learn a lot about the mass change that comes about from this size spacecraft going at the velocity that it will be going, about 15,000 miles per hour relative to Dimorphos. And so that's all to come. That impact, you folks probably have already seen or read this somewhere. Orbital mechanics is very reliable. It'll happen at 7:14. coming up here in 13 days. Here's something that you folks will understand quite easily. It's the same as we use to find exoplanets around stars. It's the favorable geometry of a binary or a multi-body system where the smaller body passes in front of the larger one, and therefore the high part of the light curve is the sum of the two, and the lowest part is when the small body passes in front, and the higher part is when the small body passes behind, and it happens over and over again as long as the orbits aren't perturbed, which we hope to do. And so that's now 11.9 hours or so, and a whole bunch of ground-based telescopes over the period of 20 and 21 did in fact locate and look at the light curve of the double asteroid system. So we have a lot of confidence in that. Now, it got far enough away from us in its 2-year orbit between that time and now that in July, we got close enough again that about half a dozen of these telescopes, including Lowell, acquired it again as it got close to its closest approach, which is coming up in September and early October. And so they measured it again after I got these slides a couple months before that, and they did verify the orbit again. It hadn't changed. And so we're looking forward to see who, after the impact, is the first one to report accurately the change in orbit. And I imagine there will be a bit of a competition there. At any rate, what's going to happen is this. We're going to hit it. We expect that there will be some crater, and a crater creates material, ejecta, that of course go out in the opposite direction of the impact. And you remember from Newton's third law of action-reaction, if you have material that comes out in the opposite direction, that adds to the change in the momentum and the velocity. And so the combination of momentum transfer from a small mass hitting at a high velocity and what comes up from the ejecta is what we're going to be trying to understand. So on the right there, or on the left rather, there's the example with no ejecta. There will be some change in its velocity. If we get a small crater with some ejecta, there will be some. And if we get a larger crater with more ejecta, there will be more added boost from what's called beta. We've, of course, computer modeled this as the surface of a small asteroid that's a rubble pile, which is nothing more than grains to small rocks to larger rocks to medium to very large. And so you see with that model and the impact, they've calculated that maybe it'll be a 15-foot across, 10 feet deep crater with that amount of ejecta. So we're going to see what happens when it actually happens. Since this was designed, it'll be interesting to see if this comes through the way they expect it to. That model was from quite a few months ago. And since then, you may remember hearing of Bennu, the NASA OSIRIS-REx spacecraft went there 2 or 3 years ago, I think it was, went down to the surface, as you'll see in a minute in a video, and didn't crash into it, but sampled the surface with a compressed gas burst, collected a sample, which is now on its way back to Earth and will re-enter, I think, maybe late this year or early next year. So we'll get a look at some actual material from Bennu. And so we've gone back and looked at the crater that was created by that air blast, and you're going to see that it was quite a bit different than what had been predicted. And I'll just show you what that was. But at any rate, the asteroid itself is a bit smaller than Didymos, but much larger than Dimorphos. And so we're talking about in this next slide that I'm going to show you that shows what happened on the surface of Bennu, an asteroid that is also a rubble pile, but it's much more massive and therefore it has much higher gravity to hold the stuff together. And so hopefully this will work well. What you see here are actual images. We orbited Bennu for a while before we went to pick the site to go down to, and then you'll see the artist concept of how it was supposed to work in a second here. So this is now an artist concept. And the foot on the bottom has got the ability to explode gas, as you will see. Again, just an artist concept. Kick up a bunch of material. They estimated how much would get kicked up. Got collected in the top of the foot, closed up, put into a re-entry capsule and sent back towards Earth. So that's a real picture. Now here's the actual image of what happened. Much more explosive, much more material was kicked up and a much bigger crater than they ever expected. They went back and took a look at it quite a long time after. And so what they have now concluded is that the cohesion of the surface layer was essentially non-existent. Where we have, with liquids, surface tension holding things together, and even with clumps of, powder, stuff clumps together, you have a certain amount of cohesion. What we found with the explosion of the surface and the amount of material that was blown away was that we had something that looked more like this. Now, whether that will mean on the upcoming, and an example of that is how balls move aside when the kids dive into the, whatever it's called, a moon bounce, I guess, or something. And so it turned out to be quite a bit different. And the way they put it was that it was nothing like they expected. And this was a report just a couple months ago, long after I got these other slides from the DART team. They said on Bennu, the surface flowed away like a fluid. So that was a lot higher, gravity. We're going to see what happens now with Dimorphos, and I hope that they actually do get some ejecta. It could be quite a useful test in that sense. So that's what's coming up. Here now finally is what the spacecraft looks like, a simplified view with the important elements labeled. That all important Draco telescope there. You see the dimensions about a little over 6 feet in diameter and 8 to 9 feet tall. The Lichia cube is on the side there. We'll talk about that in a minute. You flip it 180 degrees for the view in the center, and you see the hydrazine thrusters that are going to be used to correct the trajectory as it heads in, and then center on Dimorphos. And the image will be real-time sent back, and we'll be able to watch this through that high gain antenna you see on the side, and you see the dimensions there on the right. So I wanted to give you a feeling for just how big, or maybe how big, it is, or maybe how big it's not. It's only about the mass of a little bigger than or a little less than a smart car. Another way to look at it, you see it standing there in the clean room, wrapped up and ready to go. You can't quite tell what the size is. And so I thought I'd show Shaquille O'Neal standing next to it, and he can place his palm on the top of it. So that's how tall the spacecraft is. And it weighs about 3 or 4 times as much as him. So now you have a picture of 3 or 4 Shaquille O'Neals smashing into an asteroid here in a couple weeks. The Lichia cube is one of the literally thousands of CubeSats now that have been launched. They are quite standardized as opposed to other small sats. They're a particular kind of small sat. The U factor is about the size of a box of Kleenex, like this, about that size and shape. And so a 6U, which is what Lichia Cube is 3 of those next to each other with a row of them on top of that. They will, it will be deployed about 10 days before coming up here in just 3 days. And it will have its closest approach about 3 minutes after the impact. And there are 2 telescopes, or 2 cameras rather, which the Italians cleverly named Luke and Leia. And the Leia is the one with the high res look. And Luke will give us hopefully some composition information from the multispectral information. So that's what's coming. The operations will rely on the Draco, the Didymos Reconnaissance and Asteroid Camera for OpNav, a wonderful acronym there. And for you folks that like these things, it's actually a telescope with about an 8-inch aperture and a field of view of 0.29 degrees. And as you'll see in a minute, it's already operating nicely. Here's the timeline. So we're past the 30-day point at the 27th of August. It says, and remember, these are slides that are 6 months old. At that time, it said that we would, at that point, start to detect the Didymos system. Here's an actual image taken by Draco, and it was taken about 30 days before then. So they stacked a bunch of Draco images and could make it out there. You may have seen articles about this in the last week or so. They've been in different journals. And so at 10 days, the ground antenna will be turned on the RF system so that we'll get continuous coverage from that point on. It'll be well within the last day when we actually start to go into the automated phase, the terminal phase, where between what Draco sees, what those hydrazine thrusters can do to aim the spacecraft, and what the software can do, we're going to aim hopefully at the center of a dimorphos asteroid that until the last hour, we won't actually have seen at all. At about an hour before impact is the first time that it'll fill more than a pixel of the focal plane of Draco. At that point, it's about 15,000 miles away and you're an hour away, so it'll hit it at 15,000 miles an hour. Here's a nice computer simulation of what goes on there. And so in the yellow box, you see the image that will be sent back to Earth continually. You see it blown up on the left, and you see how the thrusters will be used to try to keep the spacecraft centered on at this point, that far out. They won't yet be centering very easily on Dimorphos, but you can see the offset point grow as they're able to see Dimorphos more clearly. And I'm going to move this forward, even though it's speeded up, it's an hour of simulation. So let's go down here within the last 2 minutes. And at this point, we're actually, as you see, moving in and centered only on Dimorphos. Very little need for the thrusters as we kind of tweak the aim and aim right for the center of it. And at that point, we'll actually have our first actual view of what the asteroid really looks like. So not very exciting to see that way. As I said, that'll be at 7:14. If you folks want to watch this, there's live coverage starting at 6 p.m. that evening on NASA TV. And if we could get up there and watch it up close, sort of a God's eye view, this is what we get a chance to see. And hopefully a substantial crater and substantial ejecta, and then Lichia Cube will fly by and take a look at it. So that's our part of what you can now see at the top there is actually an overarching international program with that long name. AIDA. And the second spacecraft is from the European Space Agency, and we won't talk about it at any length. It's that block of cheese looking thing you see there, and it's known as Hera, and it'll be launched in 2024 to the same small asteroid. It'll rendezvous as opposed to impacting with it. And the purpose of it is, having gotten some information, hopefully from the change in the orbital period, and also from imagery from LiCheCube, we're going to get a much better crime scene or crash scene investigation from Hera. It's going to measure the mass much better with the thermal and optical, and it's also got a LiDAR, which is very useful for topography. There'll be CubeSats. They haven't firmly decided on and built those yet, but there'll be multiple CubeSats to get real close to the surface to see the ejecta, measure, and hopefully be able to tell what kind of materials we have and what the surface is like. And one of those may land on the surface. So that's all coming up. I wish it were going to be faster, but we'll get the final information about 4 years from now in 2026 from the ESA spacecraft. And so we'll finish with a picture of the rock group Queen. And some of you may recognize Freddie Mercury there in front. And of course, the reason I'm showing this, some of you may know, is because this guy there, lead guitarist, is also an astrophysicist, a British astrophysicist named Brian May. And here's Brian today. He's a pretty well-known NEO scientist, and he's in the news quite a bit. And he actually, I'm showing him here looking as he does like an English barrister from the 19th century. He narrates the European Space Agency video about Hera, and it's a really, really good video. And so there's a very long web address. I'm going to give Don a copy of a couple slides, so you guys don't need to write it down. You'll get it from him. The other slide I'll give him is this one. That shows where in the sky, if you guys want to do some astrophotography. You can't see it with your telescopes, but you see the information on the left here from the Minor Planet Center telling you if you want to do some, stare at it for a bit, you can actually see it there in the region of Columba is the constellation south of Orion, south of what's it called, Lepus. So that's where it'll be. Unfortunately, nobody's going to get a look at it actually happening with a telescope, but you can see the double asteroid system if you want to try to. So that's it, folks. Any questions?
What's the time delay between Earth and Didymos at the time you're going to have the impact?
Let's see, I'm going to have to ask you to repeat it because I had my sound turned down because those animations had sound to them. Go ahead.
The time delay between.
For a transmission between the spacecraft and Earth, how long would that transmission take at the time of impact?
It's about 6.7 million miles. So take 186,000 miles per second, and somebody can figure that out. I don't know. What is that? How many lunar distances? 25? I'm not sure. Has anybody figured it out yet? It's let's see. The sun's 8 minutes, 7 million. It's about what 1/13th, 1/14th. So what, 30 seconds, something like
Less than a
that.
minute. Less than
Yeah.
a minute.
Not long.
All right, thank you.
Hey, John, it's Don North.
Nice job.
Thank you.
As far as the approach, is it in the orbital plane of the minor satellite? And will it accelerate the little, the little asteroid, or is it going to slow it down?
It will shorten its period. So
Goes ahead down
so-
the ballistic.
slow it down. Yeah. It'll shorten its period by, they hope, at least 6.5 minutes and as many as 11 or 12. But again, it's going to be very interesting to see. I'm concerned that it's not going to have the impact that we hope it will. No pun intended. If the surface is as soft as it was on Bennu, I'm not sure what they're going to find, because that looks more like energy absorption than it does ejecta, reaction. We'll see.
Actually shot right through it. Then you probably get a much more of a minor effect, right?
Yeah, for sure. It's 100. You saw that picture that showed it going into the asteroid, the animation, that was fairly true. It's extremely small relative to the size of the asteroid. It's 2 meters. The asteroid is 160.
John?
Yes.
Did you get any information at all about why they could pick this particular type of system to test this on?
It's interesting that the ambassadors that were online with me, nobody thought to ask that question. I've gotten that question before. I've given this talk a number of times now. It's a very good question. Clearly, it's because it was in a size range at 160 that fits nicely in the ones at about the point that we're really worried about them. So it's the ones where we want to exercise the kinetic impact technique. So they were searching for ones that could be candidate targets. It is a binary system, and therefore the ability to measure the momentum and velocity change by measuring the orbital period change directly is very attractive, and it had a favorable geometry such that we could do the measurements by seeing the light curve change. If it had been inclined, say 30 degrees, we wouldn't have been fortunate. So I imagine they had a limited number of candidates, and they picked it based on things like that, but I actually don't know, and nobody asked the APL guy that talked to us.
I was just curious about that because I was wondering if I can see for data collection why they chose the system, but were they also perhaps thinking in safety considerations that if the thing really did actually have a huge impact on it and really broke this thing apart, it's still kind of tethered to that asteroid, at least in part, so that you won't get ejected going, or at least a lot of ejected going where you don't expect it or don't want it.
Was that a question? I didn't follow you, Dave.
In other words, that small asteroid, even if you broke it up into a few bits, it's still gravitationally tethered to the much larger asteroid in that binary system. It kind of
Right.
gives you a safety factor.
That's, you know what? You're exactly right. You're exactly right. And you just reminded me, in another group, we came up with that also. You're right. That's very much the case. Didymos is not threatening Earth at this point. It's in a range approaching 1 kilometer where it would be very dangerous if it did. And Didymos itself will have its orbit impacted not at all by this impact. And so, as you said, Dave, it'll stay right there. It's not going to deorbit and hit us.
I was just wondering if, I was just curious if that was actually why they chose this kind of a system to test the system first on, rather than just say, putting a bunch of CubeSats out there in the path of a single asteroid and then just doing measurements over a period of years after the impact.
Certainly you could do that. This gives you that wonderful satisfaction of getting an early result from the change in orbital period within the first few days.
Thanks, Sean.
Good
John,
question.
this is
Yeah.
Sue Johnson. It seems to me, I think you implied this, that a mission like this was planned well before we had an idea that of the variation in the composition of asteroids. And so was the assumption that asteroids were made up of sort of more solid rocky material than we now realize may be the case from the Bennu example?
No, in fact, it's been long understood that they're rubble piles. And Bennu, and this is based on what I read of the NASA Goddard article about it just in July, I think, it was a huge surprise to them.
Right.
What isn't a surprise to them or me, or shouldn't be a surprise to any of us, is the asteroids are enormously variable. And
Yeah.
we know a collective amount of a very small percent of what there is to be known about them. And every test is going to, give us another, not just 1% of information, but probably add a lot to it. So anything could happen. And this could be, could be that the surface will be a lot more cohesive, crustier than it was on Bennu. It could be that what that will be will give us 2 data points about the variation in asteroid crusts in a certain size range. There's just so much to be learned.
Right.
And we're going to learn about whether this one is got a thicker crust for some reason. If it does, that won't necessarily teach us that every small asteroid of that size has a thicker crust,
Right.
or a firmer crust. So, and yet we have to try this some to see if the idea of a kinetic impact on an asteroid having a meaningful effect is going to be something that eventually we can put some spacecraft in the arsenal so that we can have them there in case there is a bad actor that we have to go after.
Right. Thank you.
Sure.
John, can you put up the date again for the impact? Or just let us know.
What was the date of the impact, John?
September 26th. 13 days.
It's in my calendar.
Mhm.
Hey, John, maybe a silly question, but are we able to tell the age of asteroids in any way?
Are we able to tell the age?
Yes.
They're all pretty much the age of the solar system. For 4.6 billion years, well, 4.5 to 4 billion years. I mean, everything that's a planet was once sort of like them. Some theories believe that because there's this big gap between Mars and Jupiter, that the mass of material there was a failed planet. It just never came together like something did in the other lanes of Mercury, Venus, Earth, Mars, and so on. But the material is that old.
Yeah, I'm just wondering if something's, how long it's been able to accumulate mass and without blowing itself to pieces, if that maybe has an impact on its cohesiveness, the surface material.
Well, I mean, gravity is very reliable, and it may have gotten to be this size and gotten to be in an orbit that isn't out between Mars and Jupiter because it was the result of a collision. That's what I think most of the NEOs have come from, the near-Earth asteroids. Objects collide out there on a fairly regular basis. The calculations of, I mentioned all those minor planets, hundreds of thousands. So we've got orbits on those. And what we've discovered from that is quite interesting of the asteroid belt asteroids, that most of them are the result now of previous collisions because they're flying in a family that has exactly the same orbital elements. And so things have broken up through the 4 billion years. And we have many, many asteroids, I think more than half of which they estimate to be parts of families from previous collisions based on the identical orbital elements.
John, Dave Hockenberry again. Just a little speculation on your part. Do you think that some of the commercial partners that NASA has are looking with great interest in what's going on here? Because much of the justification for going back to the moon and to Mars is for mining operations in the asteroid belt in the future. There are a lot of interesting minerals out there. Do you think that they're kind of watching this with sort of a curious eye as to how you can actually extract stuff out of asteroids by impacting?
You know it. I mean, there are actually some companies now that have stated that in their mission that are startups. You know, it's going to be maybe have an intentional pun. It's going to really have a first mover advantage. But it's going to be a while yet before we come up with ways to, as a matter of fact, I think the company I read about is looking at how we can deorbit some of the more interesting asteroids to bring them down closer to Earth where they can go up and rendezvous with them without having to go way out there. There are all sorts of concepts. Yeah, there are lots of people thinking about that now. The Chinese, I think, just announced 3 more lunar missions. Maybe what some of you have read this too. What they've learned in that South Polar Aitken Basin region, you remember I talked about that in our lunar talk, on the far side, down toward the South Pole. They're the first people to go there, and they're being apparently not completely open about what they're learning with their rover. And maybe the fact that they have announced 3 more lunar missions to that area, I have no doubt that they're planning to go look for minerals and stuff there. And I think we are too, with our planning for what Artemis is going to lead us to be able to do.
So do you think the next ship that'll be out to the asteroid belt will be named the Nostromo?
There you go. It makes me think about, I know Don has seen this. I don't know how many of you have watched The Expanse, but if you want to have fun thinking about asteroids, you have to watch that, stream that particular show. You've got 3 species of humans: Martians, who are the Earthlings that went to Mars, and their physiology has changed so much in the centuries that they're different. And you've also got Belters, who live in the asteroid belt, who also have different physiology, and the Earthlings, of course. But it's a fun way to think about. It's got some pretty accurate things in it at times about the asteroid belt.
Thanks, John.
So I enjoyed this. I wish Bruce could have joined us. I don't think he's able to be here tonight. But at any rate, what's that?
Bruce had some family obligations.
Yeah. Well, I appreciate your folks letting me do this via Zoom. I hope to see you physically before too long.
Thanks for taking the time away from your vacation and your family. It was great.
Not at
Yeah.
all.
It was a great presentation. Thank you.
Thanks very much.
Yes, thanks, John.
Anything else?
John, thanks again for another fantastic presentation. And in 4 years, we'll perhaps have an update on this one to see just what this little impactor did.
Exactly. See if I can figure out how to undo this now. You want control back. Stop sharing. All right. Goodbye, everybody.
Bye-bye.
Bye.
Very good.